Last time we talked about a design recipe for assembly programs, and today I want to do a couple more examples of going through that design recipe and writing assembly programs. So my first example today is going to be the Collatz conjecture. So we're going to write a computer program that's going to try to do simulations to test this conjecture. And so, of course, the first thing that I need to do is explain the thing. So the idea is we are going to take an integer, and then if that integer is even, then we're going to divide it by 2. Otherwise, we're going to take the integer 3 times x, yes, I have 2 x's, plus 1. And the famous conjecture here is that if we iterate this operation of if the integer is even, we divide by 2, if it's odd, we multiply by 3 and add 1, repeatedly, no matter what integer we start with, we will eventually end up going down to the number 1. Now there's sort of 2 possibilities here. If we start with a number and iterate it, either it's going to get smaller and smaller and eventually hit 1, or we're going to have some cycle that occurs in integers. To see what I mean by that, let's look at some quick examples of starting with numbers. So if we start with 5, 5 is odd, so we're going to multiply by 3, that's 15, add 1 is 16. 16 is even, so we divide by 2, that's 8. 8 is even, so we divide by 2, that's 4. 4 is even, so we divide by 2, that's 2. 2 is even, so we divide by 2, that's 1. So 5 is an input where we end up at 1, which is the what the conjecture says we'll always end up with. Now you'll note that once we end up with 1, we could keep going. So 1 times 3 plus 1 is 4, which would give us 2, 1, and then that cycle 4, 2, 1 would repeat forever. So once we get to 1, we know we're in that 4, 2, 1 cycle, or we could define it so that we stop at 1. But in any case, if we start with 5, we do eventually get to 1, and we get there in 1, 2, 3, 4, 5 steps, just coincidentally. If we start with 7, let's see what happens. So we're going to go 7 times 3 is 21, plus 1 is 22. 22 divided by 2 is 11. 11 times 3 is 33, plus 1 is 34. 34 divided by 2 is going to be 17. 17 times 3, I can't do arithmetic. 17 times 3 plus 1 is 52. Is 26. Is 13. Is 40. Is 20. Is 10. Is 5. And then that brings us to the sequence that we got before starting at 5. And so we see that although in both of these test cases we do eventually end up at 1, in the 5 case it takes 5 steps, whereas in the 7 case it takes 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It takes like 16 steps. So what we're going to do with this program is we're going to write a program that is conceptually to test the conjecture. And so we're going to say int main And in this case, rather than actually trying to find a counterexample, what we're going to do is we're going to print how many steps it takes to get from a given input to 1. And then we could use this program to test the conjecture by running it on inputs. And if the program doesn't terminate, that means it never got to 1, and that might be a counterexample to the conjecture, although we'd have to investigate and sort of see what it's doing. So I guess actually either there are 3 possibilities for a given input. Cycles at 1, cycles at some values above 1, and there may be some input where it grows further. But the conjecture is that all positive integers do this. Cycle at 1. Alright, so our while x is greater than 1, we're going to iterate, and I guess we'll print out our number so we can see what's going on, and then we will so we're going to print out the numbers we go through, and then we're going to print out what the number of iterations was. We have some warnings. I'm going to actually fix them just so that we have a nice clean program here. So we need to include standard IO for printf, and we need to include standard lib for A to L. Then we get our actual error, which was that the name of the variable is XX. Now everything's happy. Now we can do ccall of 5. We get our sequence that we expected before. Ccall of 7 gives us our sequence of 16. 33 gives us 26. 101 gives us 25. 10,007 gives us 1,079. The sort of maximum value that we get up to was over 150,000, over 160,000. It bounces around a lot, but this is the program that we are now going to translate into assembly. And if you're feeling bored, a fun thing to do is to modify this program so that it actually searches more, like automatically searches the space of integers, and try to find a counterexample to the conjecture. Good luck on that. But right now we're just going to translate this testing program into assembly. So to do that, I'm going to copy our C program into an assembly program, and then we are going to edit the assembly program. So I'm going to comment out the 2 functions. We're able to translate the 2 functions separately. We'll start with the top one. Global main. We have our text section. In our text section, we're going to have our iterate function. So iterate is a function. We're going to leave with return. But we've forgotten our recipe. So recipe, signature, it's right there. Pseudocode, it's right there. We need to do variable mapping before we can do variable mapping before we can write the skeleton or the function body. So the first variable we need is the argument x. And then the question is, does x need to survive across any function calls? Are we required to use a safe register? The answer is there are no function calls in the iterate function. This is a leaf in the call graph. And so for a leaf in the call graph, we can safely use a temporary register. X is our first argument to the function. So we can just go ahead and assign it to stay in the first argument register the whole time. So we're going to say enter 0, 0 and leave, because there are no other variables here. Now, the first thing that we do here is we need to translate the if. So for an if, we have a relatively consistent pattern. We're going to have a condition. Then we're going to have a then scenario. We're going to have an else scenario, and because that if is the only thing that happens in the body of the function, we can have a done label, and that'll be all the places we potentially have to jump. So now we have to translate this condition. The condition depends on a integer mod. So we're going to go ahead and do an idiv, and we want to divide by 2. So I think we can put in a literal 2, but we've got to move RDI into RAX. So then idiv will divide by 2. And then our question is compare the remainder. Now if we go look at the idiv documentation, we'll see that the remainder ends up in RDX. We're going to compare that to 0. And then if it is equal, we're going to jump to then. Otherwise, we're going to jump to else. Now in this then case, what we need to do is we need to return x over 2. But it turns out the code to do that is pretty short. We don't need to do anything. Our return value is already in RAX. And actually, that means we could optimize away this entire then label. We could have this JE be jump to done, and that would do the right thing. But I'm going to leave the pattern here for the if then else thing, just for a better example of the translation, because we don't need to be optimizing compilers. We can just be simple compilers, and that will be sufficient for this class. In the else case, we have to do a little bit more arithmetic. We have to do x times 3 plus 1. So we're going to mov RDI. Oh, RDI is already in. No, it's not. We need to put it in RAX because RDI still has the original value of x, not x over 2. Then we're going to do an imul of 3. Result is in RAX. And then we're going to do an inc of RAX. And that's going to leave our correct answer in RAX when we then return it, when we go to iterate done. Now, one thing that I am suspicious of, we'll find out when we try to compile this, is that it may be the case that the idiv and imul single argument instructions do not support having literals, and we'll find that out when we try to compile it. We could go look it up, but the two possibilities are it supports it or it doesn't support it, and if it doesn't support it, we can go ahead and work around it in a second. Let's go ahead and do main. So here again we have signature is right there, pseudocode is right there. Now we need to do variable mapping. So we have argc, argv, xx, II, and that looks like all of the major variables that we have in this function. So argc never gets used. I'm not even going to bother mapping it. We probably should be checking for usage, but it didn't show up in the pseudocode, so we're not going to do it in the assembly. argv is only used in one place, which is as the argument to a to l, so it does not need to survive any function calls. So we can go ahead and leave it where it showed up, which is in RSI. X does need to survive function calls. Specifically, it needs to survive printf and iterate. So to simplify things, we are going to put XX into a safe register. I'm going to use R12. Similarly, II does need to survive function calls. In fact, it's the same too. It needs to survive that printf and that iterate. So we're going to put this in a safe register, R13. Now that we have our variable mapping, we can do our skeleton. So main push R12, push R13, enter 0, 0. Quick, can we enter 0, 0? Why? You should know the answer to this. We can enter 0, 0 because we're pushing 2 registers, which means that we're going to move the stack down by 16. So without any pushes, the stack would be aligned at a 16-byte boundary. We have 2 pushes, it's still aligned at a 16-byte boundary. We're not doing any direct stack allocations, so enter 0 is fine. Leave, pop R13, pop R12, ret. Function body, mov 8 RSI, that's argv sub 1, into the first argument register, call a to l. Now we need to move that to x, which was R12. Next line is mov 0 to R13. And then we'll do our while loop. So a while loop is going to have a label for the condition. So every time through the loop, we have to check the condition before we decide if we do the loop body. And then we need a second label for when the loop is done. So at the condition, we're going to decide whether or not we're going to do another iteration, and if we're not, we're going to jump to the end of the loop. The bottom of the loop, we're going to do an unconditional jump back up to the top. So if we get into the loop, we execute the loop body, and then jump back up and recheck the condition. The condition is just x, which is R12, greater than 1. But the question is not whether we want to continue the loop. The question is whether we want to finish the loop. So rather than using greater than, which is the condition that appears in the C code, rather than using greater than, we're going to use jump LE less than or equal to decide if we want to jump out. So there is our loop condition. We do the comparison and then the conditional jump. In the loop body, we're going to mov R12 into RSI. We're going to mov our format string into our DI, move 0 into AL, and then call printf. So we're using this long format. That's going to be this string up here in printf. So down here we want our data section. And long format 2 is going to be with the II equals text. So after our printf, we want to mov R12 over to RDI, call iterate, and then mov RAX back to R12. So that's this line of code up here where we're going to call iterate and assign the output of iterate back to our XX variable. Finally, we will inc our II, which is R13. So there's our loop body. After the loop body, we want to call printf again, except it is long format 2, and instead of printing XX, we're going to print II. So there is our completed first attempt at the assembly. Let's go ahead and try compiling that. Turns out we get our operand type mismatch for idiv and imul. So as I suspected, there isn't a variant that uses a literal. So we're going to go ahead and just assign another register for that, the 2 here and the 3 down here, since we can't pass literals. We'll use R10 because that's one of our 2 completely unused temporary registers. So we'll move 2 into R10 and then use R10 here. We'll move 3 into R10 and then use R10 here. With that, it now assembles, and we can do call as of 5, but we get our floating point exception. Well, remember from before when we did idiv, the thing that was causing floating point exceptions was overflow, and that was frequently because it's taking 128-bit input, and the top bytes of that are in RDI, so we can use the CQO instruction to sign extend RAX to RDX, which for a positive number means zeroing out RDX. And with that, suddenly we are having a working Collatz conjecture example. And this should produce exactly the same behavior as the C program, because I think we did a relatively effective translation. All right, so that was one example. Next video will be another example, I think.